Swayam Prabha. Digital India. Educated India.
So far we have discussed graphical methods for kinematic synthesis. Today we shall start discussion on kinematic synthesis of planar linkages, but by analytical methods. If we recall, we discussed 4 different types of problems when we had graphical methods, namely motion generation, function generation, path generation and generation of prescribed dead center configurations. However, when we discuss analytical method, we shall restrict ourselves only to one type of problem, namely function generation. There are various methods like analytical methods for function generation, but we shall discuss only one such method, which is known as Freudenstein's method. As an example, we take a 4R linkage function generator and show how to design, that is, how to get the link lengths for generating a prescribed function. If we remember, when we discussed graphical methods, we had function generator for 3-position synthesis and 4-position synthesis. However, we shall restrict ourselves only to 3-position synthesis so far as 4R linkage function generator is concerned. As we shall see later, for 3-position synthesis, we can get away by considering only linear algebraic equations, which are very easy to solve. Towards this end, let me first draw a 4R linkage . These are the 2 fixed hinges O4, O2, which defines the fixed link, and we take our x-axis joining O4 and O2. O2, A, B, O4 is the 4R linkage, where O4, O2 is link number 1, that is the fixed link. O2A, the input link, is link number 2. AB is the coupler, which is link number 3, and O4B, the output link, is link number 4. the orientation of the input and output link is defined by the angle that they make with x axis, namely theta 2 and theta 4. We complete the coordinate axis by drawing the y axis with O4 as the origin. For 3 position synthesis, what we mean is to generate 2 pair of prescribed coordinated movements of the input and output link. That is, as the input link goes from position 1 to 2 by changing theta 2 by an amount theta 2 1 2, the output link should move from position 1 to 2 by a prescribed movement theta 4 1 2. Similarly, another pair of prescribed movement is theta 2 2 3 and theta 4 2 3. So, from position 1 to 2, change in the angle theta 2 is given by theta 2 1 2, and the corresponding change in the angle theta 4 should be theta 4 1 2. This is a pair of prescribed movement, and this is another pair of prescribed movement, as theta 2 changes from second to third configuration by an amount theta 2 2 3. The corresponding change in theta 4 should be theta 4 2 3. In Freudenstein's method, for this 3 position synthesis, we assume the values of theta 2 corresponding to the first configuration and value of theta 4 corresponding to the first configuration. I would like to emphasize that you should note the difference in the assumed parameters so far this analytical method and the previous graphical method is concerned. In the graphical methods, what we assumed is the location of the point A, that is corresponding to the first configuration, that is the link length L2 and theta 2 1, or we could have assumed the point B corresponding to the first configuration, which means assumed is L4, the follower length, and theta 4 1, whereas here we are leaving the link lengths as unknown parameters and we are assuming the values of theta 2 and theta 4 corresponding to the first configuration. This gives me theta 2 2, which is theta 2 1 plus theta 2 1 2, and theta 4 2 is theta 4 1 plus theta 4 1 2. These are already prescribed, these we have assumed, so we get these 2 values, namely theta 2 2 and theta 4 2. Exactly the same way I can get theta 2 3, which is theta 2 2 plus theta 2 2 3 and theta 4 3 is theta 4 2 plus theta 4 2 3. So, once we know theta 2 2 and theta 4 2 and we are given theta 2 2 3 and theta 4 2 3, I can get the values of theta 2 and theta 4 corresponding to the third configuration, namely theta 2 3 and theta 4 3. So, the 3 position function generation has boiled down to determining the link lengths such that these 3 pairs of values of theta 2 and theta 4 can take place in this linkage. As a first step towards Freudenstein's method, we obtain the displacement equation in a particular form, which is known as Freudenstein's equation. First, we derive Freudenstein's equation, which is nothing but the displacement equation for this 4R linkage in a particular format. Towards this end, we note that the x coordinate of the point A, x A, is given by L1 plus L2 cosine theta 2, where L1 is the length of the fixed link O4 O2, this is L1, and O2A is L2, AB is the coupler length L3, and O4B is the follower length L4. The y coordinate of the point A, YA, is easily seen to be L2 sin theta 2. And the x and y coordinates of the point B, namely xB, is L4 cosine theta 4 and YB is L4 sin theta 4. So, the distance between these 2 points A and B I can write, which is L3, as you see, the square of the distance L3 squared is simply XA minus XB whole squared plus YA minus YB whole squared. Substituting for XA, XB and YA, YB in here, we get L1 plus L2 cos theta 2 minus L4 cosine theta 4 whole squared plus L2 sin theta 2 minus L4 sin theta 4 whole squared. Expanding this, we can easily get L1 squared plus L2 squared plus L4 squared plus twice L1 L2 cosine theta 2 minus twice L1 L4 cosine theta 4 and minus twice L2 L4 cosine theta 2 cosine theta 4 sin theta 2 sin theta 4, which gives me cosine theta 2 minus theta 4. We rewrite this equation cosine theta 2 minus theta 4 is divided by twice L2 L4. So, L2 and L2 cancels, we get L1 by L4 cosine theta 2 minus L1 by L2 cosine theta 4 plus L1 squared plus L2 squared minus L3 squared plus L4 squared divided by twice L2 L4. We write L1 by L4 as a design parameter d1 cosine theta 2, L1 by L2 another design parameter d2 cosine theta 4, and this quantity we write as another design parameter which is d3. And this equation is called the Freudenstein's equation. This equation is called the Freudenstein equation, where three design parameters are D1 is equal to L1 by L4, another design parameter D2 is L1 by L2, and the third design parameter D3 is L1 squared plus L2 squared minus L3 squared plus L4 squared divided by twice L2 L4. Now, this equation has to be satisfied by these three sets of theta 2 and theta 4 values. Theta 2 1, theta 4 1 I can substitute, then this equation will be satisfied. If I substitute theta 2 2 and theta 4 2 for theta 2 and theta 4, then also this equation will be satisfied, and I can also substitute theta 2 3 and theta 4 3 in this equation. So, this way I get three equations which are linear in three design parameters D1, D2 and D3. Because the values of theta 2 and theta 4 are known, the only unknown in these three equations are D1, D2 and D3. And this equation is linear, so I can easily solve for three unknowns, namely D1, D2, D3, by substituting these three pairs of values of theta 2 and theta 4 in this equation to generate three equations. And this is what is known as Freudenstein's method of function generation for three position synthesis by a Fourier linkage. Now, thing to note is, from these three design parameters, once we have solved, I can get the link length ratios, namely L1 by L4 from D1, L1 by L2 from D2, and substituting for L2 and L4 in this equation from D3, I can get L1 by L3. So, the three link length ratios, namely L1 by L2, L1 by L4, L4 and L1 by L3. These three link length ratios can be obtained by solving a set of three linear algebraic equations involving D1, D2 and D3. At this stage, it may be worthwhile to recall that after solving this set of linear equations, D1 may turn out to be negative, so is D2. D2 may be positive or negative, D1 may be positive or negative. What does it imply? The negative values of D1 and D2 imply that this L2 and L4 has to be interpreted in the vector sense. That means, if L2 turns out to be negative, that means this theta 2 is theta 2 plus pi, such that L2 becomes negative. Similarly, L4 also has to be interpreted in the vector sense, that if L4 D1 is negative, then L4 is negative, which means theta 4 will be changed by theta 4 plus pi. L1 we should always take as positive, and we will take L3 also as positive by solving L1 by L3 whole squared from this equation and taking the positive root of this L1 by L3. So, to summarize, I can say that fixed link length and the coupler length always positive. If D1 turns out to be negative, that means L4 can be negative, and if D2 turns out to be negative, then L2 is negative. So, L4 and L2, that is the input link length and the output link length, may be positive or negative. The negative link length has to be interpreted in the vector sense, that is, we have to think of this O2A in this direction, that is theta 2 changes by theta 2 plus pi. Exactly the same is true for the output length. If L4 is negative, then O4B will be in this direction, that is theta 4 has to be replaced by theta 4 plus pi. I would also like to say that sometimes maybe the input link is on the left hand side and the output length is on the right hand side. That means the 4-bar linkage may be in this configuration. This is input link, this is the coupler, this is the output link, and this is the fixed link. It is easy to see that in such a situation, I take my x axis again along the fixed pivots, that is along O2, O4, and y axis perpendicular to that. This is theta 2 and this angle is theta 4. So, we get Freudenstein's equation to corresponding to this 4R linkage exactly from this equation only by replacing theta 2 by theta 4 and L4 by L2 and theta 4 by theta 2 and L2 by L4. Here of course, L2, L4 interchanging is not changing this at all. Only D1 and D2 will be changed, D3 remains the same. So, this equation will be cosine theta 2 minus theta 4 will be L1 by L2 cosine theta 4 minus L1 by L4 cosine theta 2 plus D3. So, we define L1 by L2 as one design parameters and L1 by L4 as another design parameter, like the situation we faced here. So, that is the Freudenstein's equation and this is the Freudenstein's method. As explained just now, for 3-position synthesis, we write Freudenstein's equation in this form. Cos theta 2 minus theta 4 is d1 cos theta 2 minus d2 cos theta 4 plus d3, and theta 2 and theta 4 takes 3 pair of coordinated values, namely theta 2 1, theta 4 1, theta 2 1, theta 4 1, or theta 2 2, theta 4 2, theta 2 2, theta 4 2, and theta 2 3, theta 4 3, theta 2 3, and theta 4 3. That gives me 3 set of linear equations in d1, d2, and d3 to solve for. And once we solve for d1, d2, d3, we can get the 3 linked length ratios. It may be pointed out it is the linked length ratios that matter, because if the whole figure is scaled up, we get the same relative movement between various links. That is, the linkage remains same, it is only the scale of the drawing. So, L1 I can choose arbitrarily or conveniently, and then we can get the other 3 link lengths L2, L3, and L4. This equation can also be used for generation of instantaneous kinematic relationship, not just position but velocity and acceleration as well. Instead of generating just position relationship between the input and output link, we can use this equation for generation of instantaneous other kind of kinematic relationship between the input and output links, namely the angular velocity of these 2 links or angular acceleration of these 2 links. As an example, let us use this Freudenstein's equation to design a 4R linkage such that theta 2 is 90 degree, theta 4 is 60 degree, and at this configuration omega 2 is 2 radians per second, and at this configuration omega 4 is 3 radians per second, and at the same configuration, that is theta 2 equal to 90 degree and theta 4 equal to 60 degree, angular acceleration of link 2 is 0, but angular acceleration of the output link is say minus 1 radian per second squared. Now, how to determine the link lengths of a 4R linkage to satisfy these three conditions? When theta 2 is 90 degree, theta 4 should be 60 degree, and at this same configuration omega 2 and omega 4 are prescribed, alpha 2 and alpha 4 are also prescribed. We have to determine the link lengths. Toward this end, I start from the Freudenstein's equation for j equal to 1, that is cosine theta 2 minus theta 4 is d1 cosine theta 2 minus d2 cosine theta 4 plus d3. Since this equation is valid for all instants, what you can do, we can differentiate this equation with respect to time, and that gives me sine theta 2 minus theta 4 into omega 2 minus omega 4, where omega 2 is theta 2 dot d theta 2 dt, angular velocity of the input link, and omega 4 is the angular velocity of the output link, and that is equal to d1 sine theta 2 omega 2 minus d2 sine theta 4 omega 4. Differentiating this equation once more with respect to time, we get sine theta 2 minus theta 4 into alpha 2 minus alpha 4 plus cosine theta 2 minus theta 4 into omega 2 minus omega 4 whole squared is equal to, if I differentiate the right hand side with respect to time, we get d1 sine theta 2 alpha 2 plus cosine theta 2 omega 2 squared minus d2 sine theta 4 alpha 4 plus cosine theta 4 omega 4 squared. So, I get three equations, namely 1, 2 and 3. In these three equations, I substitute the desired conditions which are given here. If I substitute in the first equation, theta 2 equal to 90 degree and theta 4 equal to 60 degree, we get 90 minus 60, that is cos 30 degree, that is root 3 by 2 is equal to d1 cos theta 2 is 0 minus d2 cos 60 degree is half minus d2 by 2 plus d3. This is what I get from the first equation after substituting theta 2 and theta 4. Now, if I substitute omega 2, omega 4, theta 2, theta 4 in the second equation, what we get? Sine 30 degree, that is half, into omega 2 minus omega 4, that is minus 1, should be equal to d1 sine theta 2 is 1 and omega 2 is 2, so 2 d1 minus d2 Sin theta 4 is root 3 by 2. So, omega 4 is 3. So, 3 root 3 by 2. This is equation 1. This is equation 2. Now, in the third equation, I substitute all these values to get sin 30 degree is half. Alpha 2 minus alpha 4 is 1 plus cos 30 degree is root 3 by 2 into omega 2 minus omega 4 is minus 1, squared is 1. So, that is 1 is equal to d1 alpha 2 is 0. So, that term is 0, d1 cos theta 2 is 0. So, this d1, this term is also 0, alpha 2 is 0 and cos theta 2 is 0. So, this term is 0. So, we get minus d2 sin theta 4 is root 3 by 2 and alpha 4 is minus 1. So, that gives me minus root 3 by 2. Cos theta 4 is half and omega 4 squared is 9. So, 9 by 2. This is equation 3. From the third equation, I can solve for d2. After I solve for d2, from the second equation, I can solve for d1. And if d2 is known, I can solve for d3 from the first equation. If we do the algebra, we will get for this particular set, d1 is minus 0.738, d2 is minus 0.376 and d3 is 0.678. As we said earlier that d1, d2 can come out to be negative, and this particular problem d1 and d2 are turning out to be negative, which means L1 by L4 is minus 0.738, L1 by L2 is minus 0.376, and from D3, if I substitute these values of L4 and L2 in terms of L1, we can find out L1 by L3, which turns out to be equal to 0.446. So, we get all the three link length ratios, and as we said, L1, L3 are always positive. For this particular problem, L2 and L4 are turning out to be negative. So, if we choose the length L1, we can solve for L2, L4 and L3. Now, if we draw this mechanism at this particular configuration, what we see that this is O4 and this is O2. Theta 4 was 60 degree, but L4 has turned out to be negative, so I have to draw it at 240 degree. This is L4, which is negative. L2 is longer than L4, but L2 is also negative, and theta 2 was 90 degree, that is this way, so I draw it this way. So, all the prescribed instantaneous relationship will be valid for this 4R linkage, where this is L2, this is L4 and this is L3 for a given value of L1, which I can solve once I know these three values. This is what we mean by Freudenstein's method as applied to a 4R linkage. So, we have discussed the function generation problem with reference to a 4R linkage function generator with for 3 position synthesis. What we emphasize that we got linear equations in the design variables, namely D1, D2 and D3 only because we assumed theta 2 1 and theta 4 1. If we have to extend this method to 4 position synthesis, then beyond D1, D2 and D3 we have to leave one of these parameters also as an unknown to be decided or to be determined. That means D1, D2, D3 and either theta 2 1 or theta 4 1 have to be left undetermined, and then we can plug in the 4 sets of values of theta 2 and theta 4 to solve for these 3 unknowns, these 4 unknowns D1, D2, D3 and whichever is left unknown. But the trouble with that is that the equations will not be linear because of these angular term coming into the equation. We have cosine and things like that, non-linear functions of these angles. Consequently, the algebraic difficulty increases, though it can be done, but we are keeping it outside the scope of this course. So, we have discussed Freudenstein's method for function generation with reference to 3 position synthesis or 2 pair of coordinated movements. Things to remember is that after solution, input or the output length L2 and L4 may turn out to be negative. They have to be interpreted in the vector sense. Because we are assuming this theta 2 1 and theta 4 1 arbitrarily, there cannot be any solution with those values if L2 and L4 turn out to be negative, but the solution will be available if we add pi to these terms. That means L2 instead of from O2, if this is what I call theta 2 1, L2 negative means theta 2 1 I have to take this angle which is pi plus this theta 2 1. In our next lecture, we shall discuss how the same methodology can be used for function generation by a slider crank, that is the input output correlation, the slider displacement with the rotation of the crank for a slider crank mechanism.